Good day and welcome to Akai Corp. We're going today go over motor shaft grounding voltages, and we're going to start from the ground up and build up a cross-section of an induction motor so we understand all the basic components as it relates to what we're discussing. So let's get started. So the first thing we're going to add to this induction motor cross-section is our shaft, and then we'll add our rotor. That's the piece that's spinning inside the motor. And the rotor is typically made out of laminations. These laminations are basically sheets of metal that are separated by some kind of an insulator, often just a lacquer, and that's to help reduce eddy currents. From there, we're going to add our windings, very simple windings in a rotor or on a induction motor, represented here in copper color. That's one of the beautiful things about an induction motor. It's a very simple motor. The rotor rotates inside a case. In that case is the stator. The stator is also typically made with laminations, again to reduce eddy currents. Wrapped around the stator we have windings. These windings are set up in a three-phase configuration. Most induction motors are three-phase. Holding everything together we have a case. Case is usually some form of a tube, either machined or cast. And then that's held together at the end with end bells. The end bells basically go onto either end of the case. You'll notice on the one end we have a cover over the shaft. Then to hold everything together, we end up with a set of bolts. Often the bolts go right through the case and through the end bells, but for larger motors they can be just basically threaded into the case. So we're just going to pause here for a section and have you take a good look at the rotor and the stator. You'll notice that nowhere do the two pieces touch. So the stator attached to the case will be at the same potential between the case and the stator, but the rotor is not at that potential or not guaranteed to be so. We've now added the last critical piece to this induction motor, which is a cross-section of the bearings. Here we're showing the bearings, the ball bearings cut in half as a gray circle, and the races as that purple color. What is in between the race and the ball bearing is a thin layer of grease. Now that layer of grease might be only a few microns thick, but it's an insulating layer. So even though it physically looks like the rotor and the stator are somehow electrically connected, in fact, for most of the time, the rotor is riding on a thin layer of grease on the ball bearings and is actually isolated from the stator and the rest of the case. So when we tie our electric motor to ground, which is common practice, we're not actually tying the rotor to ground, just the stator and the case. So the stator and the case and the outside race of the bearings that are holding up the rotor are all tied to ground. But unfortunately, the rotor and the shaft and the inside race and the ball bearing themselves are actually an unknown voltage. They're not determined. And this is a challenge. If you take a look at a lot of the work that electrical engineers do and electricians do, it's about defining voltages everywhere in a circuit. We don't like to see stuff indeterminate because you don't know what it's going to do. And this is exactly the challenge we have with motor shaft voltages in induction motors. So I think that covers it off here for getting us up to the point where we can now talk about what that rotor voltage may end up looking like, given that it's being driven by a variable frequency drive. Thanks for watching.